Huh. Share the screen. There it is. Okay, folks, let's get started. I'm guessing everyone can hear me properly, right?
Yes, yes.
Yeah, okay.
Yes, sir.
Yeah, thank you. So let's continue with our efforts to understand the Fourier analysis. And let me give you a quick recap. So the first one that we learned was Fourier series. This is for continuous periodic signals. And if a signal is continuous and has a period t, it can be expressed as a infinite sum of complex exponentials whose frequencies are just multiples of the fundamental frequency given by 2 pi by t. Okay, so this is k times 2 pi by t. So it's 1 times 2 pi by t, 2 times 2 pi by t, and so on. So that was the first expansion that we learned. And throughout, there are only a couple of things that are needed to understand the proof. And one is this one, which is that when you integrate a complex exponential, unless this number is 0, the integral is always 0. Okay. So this was our Fourier series expansion. This is how you get the coefficients. You multiply xt with e to the power minus j k omega naught t and integrate over a period of t, which gives you the kth coefficient. Okay, and when you want to synthesize the signal from the coefficients, you just multiply each coefficient with e to the power j k omega naught t and sum all of them up, you get your signal back up to um, uh, square, so it converges in the mean square sense, which means that the energy of the error, xt minus, whatever you are reconstructing out of this, that square dt, the integral of that goes to 0. Okay, but we didn't talk about convergence. We just talked about this. And then we did an example, looked at some properties, and I'm basically only focused on convolution, the fact that multiplication turns into convolution. And we looked at Parseval's relationship. So that was Fourier series. And then the discrete version of the Fourier series, which is done for discrete time periodic signal that repeats after every n samples, that can similarly be expressed as a sum of complex exponentials with a period of multiples of 2 pi by n. Okay, so this is similar to what we had done earlier, where the period was 2 pi, the frequency was 2 pi by t. Here the fundamental frequency is 2 pi by n. However, you don't need a infinite number of exponentials, because after every n samples, they start repeating. So phi k of n and phi k plus rn are the same for any r. So you actually just need to sum over n samples. This is a very important property that we will see will come handy when we talk about this discrete Fourier transform or DFT. Okay, so this is the DFS. Formulation is quite similar. Instead of an integral, though, you have a sum here and you have a sum there as well. So in some ways, this is a very sort of dual transform. To do this one transform, you just change the sign here. Otherwise, the formulation, there's a sigma summation on both sides. So there's a neat duality between the two, and this is also seen in the frequency space. So if in the time domain you have got some signal, and you get something else in the frequency domain. So for example, in the time domain it's a rect function, and in the frequency domain it becomes a sinc. If the signal is a sinc function in the time domain, then it will likewise become a rect in the frequency domain. So there's this duality which comes directly from the way these two formulae are. They're just looking like similar to each other, just with a negative sign here and a positive sign there. Okay, and we did the proof of this also, and this relies on this particular formulation, this particular formula, and this is the integral version of what I told you earlier, and it's basically easy to prove. If you picturize this as vectors spanning a unit circle, or otherwise use geometric series progression to actually evaluate this sum. Okay, so then in the previous class, we started talking about the Fourier transform, and the Fourier transform is for continuous signals that are not periodic. Okay, and also have to have finite energy for the convergence thing to work. And basically, the idea here is that you can think of an aperiodic signal as a periodic signal with an infinitely long period. And like in the Fourier series, you needed a fundamental frequency and its infinitely, infinite multiples of that. Here, the fundamental frequency essentially becomes zero as your period becomes infinite. So you actually just need ever so finer samples, and eventually, as t approaches zero, it just becomes a continuous function. So we had looked at that interpretation also, and obtained the Fourier transform pair. And this is what it looks like. So now xt is 1 by 2 pi integral of from minus infinity to infinity of this coefficient xj omega, which is similar to what we had earlier as ak, but now it's not a function of k, it's a function of a continuous variable omega, which is given by this. Okay, and you can see the duality in this also, in the continuous version also, where the formulae just look very similar. It just has a factor here as 1 of 2 pi. In fact, if you just integrate this as f, so you just write it as x of jf e to the power j 2 pi f t, you will see that even this factor can be sort of accounted for in a way that these two become exactly dual to each other. Okay, so now we are going to move on. Oh yeah, and before we got to it, we talked about the fact that even if you have a complex exponent, a sinusoid, which is not a aperiodic signal, it's a periodic signal, you can think about it as a delta function at the frequency at which it's oscillating. And that comes directly by looking at the fact that if you have got a signal which is a a Fourier transform which has a delta function at omega naught, then the signal is just the complex exponential. It just comes from this, which uses the shifting theorem of the delta function. So this is called a generalized Fourier transform, and together this allows us to even look at periodic signals in the Fourier transform sense, in the sense that you still have a continuous frequency axis. It's just that the value is zero everywhere else except at multiples of omega naught. So which makes sense because in the discrete Fourier series case, that's what we had. Okay, and then we did a couple of properties, and now we are at DTFT, which follows exactly the same logic as the Fourier transform. Before I start that, are there any questions? Okay, so I'll take it that everyone is okay so far. So now we will do the discrete version of the of the Fourier transform for discrete aperiodic signals, and we will develop this in exactly the same way as we developed the Fourier transform. Okay, the same logic will be applied. So let's get to it. Consider a finite length discrete signal xn. So it's a finite length signal. In this case, it's from minus n1 to n2. Now, the strategy here is actually, we are going to use two strategies. So one strategy just involves making a infinite copy of the same. This is exactly the same way as we had done earlier, where we created a periodic signal. And later we will see we can think of this also as a continuous signal multiplied by a train of delta functions. So we will actually do it in a couple of different ways, which will eventually all come together and make sense. But for now, we will just do it the way we did in the previous case. So from this aperiodic finite length signal, I just make a periodic signal. Why do I make a periodic signal? Because I know how to deal with this. I can take the discrete Fourier series of this signal because it's a discrete periodic signal. And then I'll consider what happens as the period becomes infinite. Okay. So when the period becomes infinite, then essentially they become the same thing. So that's the idea. Okay, so this is exactly the way we had done earlier. So now we look at the Fourier series representation of x tilde n. X tilde n is just the periodic version of this. And if you remember the Fourier series, discrete Fourier series was right here. Discrete Fourier series was given like this. Okay, so what do I do? If this is a periodic signal, I can always sum it as a sum of n different coefficients ak e to the power jk omega naught n, where omega naught is the fundamental frequency 2 pi by n, and each ak is just given like this. It's a sum of xn e to the power minus j k omega naught n, and the proof is right here, right? So we'll apply the same logic, because this is after all a periodic signal. So what do I get? My AK, I want to find the coefficients here, is just 1 by n, x tilde n, multiplied by e to the power minus jk omega naught n over n. This is by definition. Okay, but notice that I'm doing this summation over n, where n is the total length of this period after which it's repeating, but it's the same as doing an infinite sum over xn, because xn is not a periodic signal. It just happens to be the same as x tilde n over one period, but otherwise it's always 0. So whether I sum x tilde n over one period or I sum xn over the entire period is the same thing. Okay, so this is, I'm getting the coefficients ak from this. But now let's do the same logic that we did for the Fourier transform case and define a continuous function given by this formula. Okay, so why am I defining it this way? It's the same logic that I had done in the previous class, where I had first motivated that I could think of a continuous envelope function, and I'm just looking at certain samples of that envelope function, and I had defined a continuous function given by like this. This is what I had done in the previous class. Right now I'm using exactly the same logic. I'm defining a continuous function now, like so. And if I define it this way, the coefficients that I'm looking at here are nothing but samples of this continuous function at k omega naught, where omega naught is 2 pi by n. Right? You can see that here ak is just 1 by n summation of xn e to the power minus j k omega naught n. So it's just this function evaluated at k omega naught, like so, with a 1 by n factor added in, because this thing doesn't have a 1 by n factor. Does that make sense? So I have defined a continuous function, and ak are just simply the samples of that continuous function. This is a continuous function in the frequency domain. A continuous, this omega is continuous, and I'm simply looking at, to find ak, I'm just looking at what x e to the power j omega takes at k omega naught, and I vary k from 0 to n minus 1. Okay. Now I want to reconstruct my original signal back from the samples that I have here. So what do? Well, I simply just look at, put the value back here. That's it. Oops, sorry, not the pen, but the pointer. And therefore, so I've just, this thing here is just AK. That's it. I'm just using this formula as before. And I'm just looking at this as, I'm representing it as a function of this continuous variable x to the power e j omega multiplied by this. And in particular, if I think of omega naught as 2 pi by n, okay, so I can actually make this 1 by n go away and write it as 2 pi by omega naught, and then it turns to this. Okay, so this is just using the fact that omega naught is 2 pi by n. So 1 by n is omega naught by 2 pi. So I've replaced 1 by n as omega naught by 2 pi. That's it. Why am I doing this way? Because I want to see what happens as n keeps increasing, which in turn is going to reduce omega naught. And as in the continuous case, the summation will eventually become an integral. Okay, so that is what is shown here. This is my continuous xn, x tilde n. This is, sorry, not continuous, periodic x tilde n, written now as a sum of this. So as before, if I think of x to the power, x e to the power j omega as a continuous function, and this function here is x e to the power j omega multiplied by e to the power j omega n. So this whole thing is what I'm writing as a function. The sum, this term here, is just the area of this little rectangle here. Okay, if this gets confusing, just keep in mind this is the same logic that we had done in the previous class. This is nothing, no different from what we had done here. We had defined a function, looked at the coefficients as samples of this continuous function, represented my continuous periodic signal as a sum of the coefficients multiplied by this, and just observed that this thing turns into an integral as omega tends to 0. It's exactly the same logic applied here, no difference. Okay, so this thing as omega naught goes to 0 will become an integral, but the integral is over 2 pi. Okay, and that's it. This is the discrete time Fourier transform of a aperiodic discrete signal. I can always represent the signal xn as an integral of a continuous function in the frequency domain, x e to the power j omega. It's just convention to write it like this. You multiply it by e to the power j omega n d omega and integrate over 2 pi. And to get these coefficients, you just do this, which is this formula here. Okay, so this is the same logic. Now the DTFT, the discrete time Fourier transform, is discrete in the time domain or the sample domain, but it becomes continuous in the frequency domain. And what is interesting, like in my discrete Fourier series case, is that the function, this function, the omega needs to be only defined between minus pi and pi because it starts repeating after that. If I add a omega plus 2 pi here, what happens here? Omega plus 2 pi, I add omega plus 2 pi. So if with this omega becomes omega plus 2 pi, you're just going to get this multiplied by j2 pi n. What is that? It's just a multiple of 2 pi, right? So this is just 1. So you'll get back the same thing. So this is always a periodic signal with a period of 2 pi. So it's only defined between minus pi and pi. After that, it starts repeating. Okay. So let's do an example here. Is this okay with people? Now we have done 4 transforms. They all look very similar, but some differences between each other. This is, let me just go back here. Yeah. So periodic signal Fourier series, it's continuous in the time domain, and in the frequency domain, it becomes discrete. I talk about a case. Fourier transform is continuous in both domains, and there's a very nice duality here. Discrete Fourier series is discrete in both domains, and discrete time Fourier transform is this. Okay, and there's a nice duality between this and this, as we have seen. And you will see that there's a duality between these also. So they are, in a way, very similar to each other, but you have to be acutely aware of these minor sort of, principal differences between these sort of transforms. Okay, so here I started with a discrete signal, but to represent it, if it's an aperiodic signal, I need all frequencies, much like Fourier transform, but I need all frequencies only between minus pi and pi, or equivalently between 0 and 2 pi, because it's a periodic. The DTFT is periodic with a period of 2 pi. Okay, any questions on this? Okay, so let's move on, and we'll just do an example here. So this is in Oppenheim and Bilski, example 5.1. So I've got a to the power un. So this is a function that we have seen before when we were looking at the delta, direct delta function. So it is 0 everywhere. So the function will be 0 before 0, and after that it will just look like this. Okay, mod a is less than 1. I am saying, tell me the discrete time Fourier transform of this signal. So you will first notice that this is not a periodic signal, right? So it's an aperiodic signal. So I can take its DTFT. The DTFT formula is given like this. It's just this formula here. So it's a to the power n u n e to the power minus j omega naught as j omega n. I want to find the value for some particular value of omega. And it's just a sum from 0 to infinity because un is 0 before that. And using a geometric series, you end up getting this. Okay. So if I want to plot, so this is a function of omega. If I want to plot its magnitude, this is how it's going to look like if a is greater than 0. Let's talk about this case. A is greater than 0. So what's the value at omega equal to 0? When omega is 0, this thing is just 1. So it's 1 divided by 1 minus a. That's the value at omega equal to 0. What's the value at pi? E to the power minus j pi is minus 1. Sorry. E to the power j pi by 2 is actually 0. So e to the power minus j pi is cos minus pi plus j sine minus pi. So minus sine minus pi is 0, cos minus pi is minus 1. So I'm left with 1 divided by 1 plus a. So that's the value it takes at pi. Okay, so it varies like this, but after that it is continuous. This is the amplitude of the Fourier transform, and you could similarly compute the phase. And this being a real signal, you will see that the amplitude spectrum is symmetric and the phase spectrum is odd, so it's anti-symmetric. Okay, so but that's it. That's the answer. That's the discrete time Fourier transform of a discrete aperiodic signal given by this. The same answer when a is less than 0, just the, because it's the mod here. So this is how it will look like. Okay. So no one is saying anything today. It's, are you guys still with me?
Yes, sir.
Okay. So just say yes or something so that I know that, guys are with me. Okay. So here's another example. This is the rect function. So it's 0 everywhere except between minus n1 and n1 and n1. So it takes a value 1. It's 0 everywhere else. And you compute this, and the answer will be that. Okay, so I'll leave it as an exercise for you to figure this out. It's very straightforward. So this is the sinc function in the but it has a period of pi. So omega will keep repeating after after minus pi to pi. So it does look like the rect function, except that it doesn't just go to 0 eventually on a continuous omega axis. It's a repeating axis. Okay, so you can try to prove this yourself. It's just a summation of some complex exponentials from these two limits. So it comes out very easily. And this is how it looks like. Okay, so like before, the properties of DTFT are quite similar. Linearity, time shifting, frequency shifting, these things all hold. The multiplication and convolution also hold. It's just that now the convolution has to be done over just a period of 2 pi. So it's a circular convolution, similar to the periodic convolution that we saw in the case of discrete Fourier series. Okay, so but other than that, all these properties are similar to what we had seen before. The Parseval's relationship now is an integral of this over 2 pi. Okay, because this function only varies over 2 pi. And this is the duality that I was talking about. So this is the first time we are seeing all of these together. The 4 different versions, Fourier series and Fourier transform for the continuous and the discrete case. This is the overall picture. So for Fourier continuous time Fourier series, it's continuous in time and periodic in time, but in frequency it becomes discrete. So I get AKs given by this formula here. In the case of Fourier transform, it's continuous in both time and frequency. And this duality just means that the formulae, if you look, are very similar to each other. Just a change in the minus here and a plus here, but otherwise they are very similar. So if x has a particular shape and you get a small x from there, if you use that small x in the frequency domain, you will get back the other signal in the time domain. So it's like the Fourier transform of a rect function is a sinc function, but then the Fourier transform of a sinc function will become a rect function, and so on. That's the duality because the formulae are identical here. In the case of discrete time, again there's duality here. Formulae look very same. Both are discrete. And in this case, the discrete time signal is aperiodic in time, and its discrete time Fourier transform is continuous in frequency as well as periodic in frequency. And now if you look at these two formulae here, this and this, they both, so here you are integrating over one period in the time domain here to get the coefficients. Here to get the coefficients which represent which are equivalent to the frequency domain representation. Here to get the equivalent time domain, you integrate over frequency over 2 pi. So there's a duality between this also. Okay, I'm not sure whether this is very overwhelming for you guys, but once this settles in, this is so, aesthetically pleasing that, it just gives you a high. It's just that you have to wrap around these little concepts for a while before this settles in. But, this Fourier series is so elegant in its representation and the properties that match up in the time and frequency domain so nicely that it's just a very sort of aesthetically pleasing sort of a representation. A signal can be represented in the time domain or in the frequency domain in like a almost equivalent way. So you can, as if I give you a signal, you could see it in the time domain as something that's varying, or you can see it in the frequency domain with the the x-axis turning to frequency, and the representations are very similar. The energy can be computed from either of the two. If you shift the signal in time domain, it changes in a particular way in the frequency, but similarly, if you multiply it in the time domain with something, it shifts in the frequency domain. There's a duality at every level pretty much. This sort of symmetry is there between the representations in time and frequency domain is there in like at so many levels that it's very cool. It's very aesthetically pleasing. So please take some time and make sure this settles in. Okay. So we have done the 4 transforms. Now we will move to sort of, we will get back to our problem at hand. We will now slowly move back from the theory back to the practical domain and get back to our signal and start with the Fourier, representation of the signal. So, so we will do that next with the understanding of what is discrete Fourier transform or DFT. Okay, so any questions still here? This is all okay, right? We have gone through this several times now. So now I will actually get back to a sort of more practical way of taking a continuous signal and making it discrete, and see how that can be done and what happens to its representation in the frequency domain once you discretize a signal. Okay. All right. So now we will sort of backtrack and think about a sort of practical issue, that I've got a signal like so, and I want to discretize it and look at this signal only at certain times. Now, why would I want to do that? Anyone?
Could you repeat?
Well, the question is that it's a continuous signal, but I want to only look at the signal at some time points and not the others. The question is, why would I even want to do that?
It's a wild guess, but maybe the reason is that those are points of, in the sense, those are the points which are really influencing some properties of the signal.
No, the signal is changing, and you're looking at the samples at regular intervals. You don't give any importance to how the signal is changing. You're just sampling it at some periodic interval. Why would you want to do that?
Because digitally we can only like
Yeah, that's
use
right.
digital signals like
That's
yeah.
right. So very good. So you can have a continuous signal, but if you want to show this signal to your colleague, for example, or do any analysis on it, okay, so you can't do it unless you actually store the signal in some way and then process it. Suppose you want to save it on a computer, so you want to record the signal at some suppose it's a music video, so somebody is singing, so the output of the speaker is a continuous output of the microphone is a continuous signal, but you want to save it as some mp3 file or whatever, right? So you can only save certain samples onto your disk. So each of these samples, which is a continuous real number here, needs to be converted to a bunch of ones and zeros and stored on your computer. So we'll say we are saving at 16-bit resolution or 24-bit resolution, which means we assign 16 bits to represent each of these points. But I have an infinite number of points here, so I can't do it this way. I'm just going to sample some points and save it. That's the only way for me to save it, store it, modify it, put it on my web page, and so on. We actually just deal with discrete signals all the time. So that's why we have to sample the signal. The question is that if I have a continuous signal which has a Fourier transform, a continuous aperiodic signal, and I look at a sampled version of that signal, what's the relationship between the two? Okay, so let's answer that question. So I'm got a signal like this, xt coming in. The way I can sample this is simply multiplying it with a comb function. Remember this comb function, it's a set of delta functions sitting at an interval of t. When I multiply the two, my final signal is just these delta functions, but their magnitudes are equal to the value of xt at those points. So I'm calling this XPT. It's a sampled signal. Is this a continuous signal?
No.
No, it is. Okay, so I haven't discretized it yet. It is still a function which is as a function of time t. It just happens to be 0 at most of the times, except at every 1 by t, where it takes a value equal to a delta function whose magnitude is equal to x at the value t. Okay, so this is what it is. It's the value of x at nt multiplied by a delta function at sitting at nt, and you sum all of these to get my signal back. Correct? It's just a product of these two. That's it. And this is how I'm going to represent it. Any questions on this? This is very important actually. So if there are any questions, please ask. So now I want to know that what is the relationship between the Fourier transform of this signal and the Fourier transform. It is still a Fourier transform because this is also a continuous signal. What is the relationship between the Fourier transform of this signal and the Fourier transform of this signal? So this signal has infinite energy because I'm multiplying it with delta function which has infinite energy. But if you remember, I can always take a generalized Fourier transform. So that's what I'm going to do here. What is the relationship between this signal and that signal? Now the first thing is, suppose this signal has energy over only some finite range like this. Omega m is the maximum frequency content of the signal. This is the Fourier transform of the continuous signal xt. I can take the Fourier transform because it's a continuous aperiodic signal, and I'm assuming right now that the maximum frequency content is just minus omega m to omega m. Doesn't have to be the case always, but let's assume that this is the case. Now I'm asking, what is the Fourier transform of this guy here? How do I do this? It turns out it's very straightforward. If you just remember what we had done in the last class, which is to look at the Fourier transform of a comb function. Who remembers this? What's the Fourier transform of a comb function? Generalized Fourier transform of a comb function.
Correct function.
Function.
It's a comb function. We did that in the last class. And that's the reason we had done it. See, this is what it was. A comb in the frequency domain is again a comb. The closer the delta functions are in the time domain, the farther apart are they in the frequency domain. This was previous class. I will do this again. Xt is just a sum of delta functions sitting at these. I ask, what is the kth coefficient? Okay, so this is a periodic signal now, right? So I can talk about the Fourier series of this periodic function. So it is ak, which is going to be just the delta function delta t multiplied by this. But now it doesn't matter what k is, because this thing is just e to the power jk omega naught 0, right? It just takes the value of delta t at 0 by shifting theorem. So it's just always 1 by t. Right? And then the generalized Fourier transform can be thought of as a bunch of delta functions, each of the coefficients being equal to the coefficient of the Fourier series of the periodic signal. I hope you guys remember this. We did that in the last class. This is the Fourier transform of a periodic signal. And to do that is to do a Fourier series of the periodic signal and then think of the Fourier transform as a bunch of delta functions with coefficients equal to AK, which is the Fourier series of the periodic signal. And that's what gives me this. Here, each one is just 1 by t. So it's a single train. So a comb function becomes a comb in the frequency domain. And I told you that this will come handy, and now it is coming handy. Okay, so even if you don't remember this, just keep in mind, always just keep this in mind, and half your problems will be solved. That comb in time is a comb in frequency. That is what we need to discretize a continuous signal. So, because the product here is a signal with a comb function like this, the Fourier transform is just a convolution of this signal with the Fourier transform of the comb, which is again a comb. So this comb function now is shown here. This is a frequency axis where the comb function, this is omega axis, but this omega s is just given by the how far spaced these are in the time domain, the inverse of that, right? The closer, the smaller the period here, the larger the omega. This is just 2 pi by t. But what happens when you convolve a signal with a delta function? What is the convolution of a signal with the delta function sitting at some value? It comes from directly from the shifting theorem. It just puts whatever it is at that value. Okay, so this thing will just put your original thing that you had at every omega. So it will become something like this. Okay, please take a moment to understand this. This is super crucial. This is super crucial. This is the Fourier transform of the original signal. This guy here is the Fourier transform of this sampled signal, still in the continuous time domain. So this is a continuous frequency axis. All I have done is taken this and convolved with a train. So if I convolve a signal with a delta function which is sitting somewhere, it just puts the same function at that position. Okay, so delta function at 0 will give you the thing back. If it is shifted in the frequency domain, it just shifts it. So because I have a train sitting here, it becomes like this. And depending on what is omega, if the sampling period is too small, sorry, if the sampling period is too large. So if you are sampling very slowly, then the omegas will all be very close to each other. Sorry, these delta functions will be all very close to each other. Remember, the closer they are in time, here, the closer they are in time, the farther they are in frequency. So if you are not sampling fast enough, it will become something like this. It's just going to be overlapping, and then you'll end up just getting this black trace, and you actually cannot recover your original shape. It's just got mixed in some very non-trivial ways, and you can't actually do anything. So the question is, how fast should you sample so that whatever shape you had here is sort of preserved in this. There's no like mixing of this side and that side. This mixing is called aliasing. So how fast should I sample so that there is no aliasing?
Nyquist frequency.
What is Nyquist frequency?
I've just heard this so many times and know it, but like I mean, the definition I don't have. It'll be twice the, at least twice the frequency of the
That's
signal
it.
that.
But you can see that here, right? So this is omega m. As long as omega s is twice of omega m, you're all set. If omega s is more than twice of omega m, then these two won't touch each other. So we have actually proven the sampling theorem. Okay, so there it is. This is the proof of the sampling theorem, that in order to get a signal, if you sample a signal fast enough, you can always recover the signal back from its samples. And how fast is fast? Whatever is the maximum frequency content of the signal, you sample at a frequency that is twice of that, more than twice of that. Because that makes sure that these two lobes are not intersecting, and then it is possible to recover this from that. And I'll show you how. But here's the sampling theorem. Let xt be a band limited signal with this property, that its maximum frequency content is omega m. Then xt is uniquely determined by its samples x and t. If omega s, which is the sampling frequency, is greater than twice of omega m, where omega s is given by 2 pi by t. Okay, just take a moment to just think about this. I've got a signal here. Okay, I've got a signal here. I am telling you that if I get this and this and this and this and this, I don't need to know what's between. Isn't that crazy? Just from these samples, these values here, I can always get back this entire signal just from the samples, as long as the sampling rate is fast enough, more than the max twice the frequency content of this. How do I recover the signal? It's actually trivial. If you think about it, I've got a signal xt whose Fourier transform. So here's my signal, it's continuous signal. Its Fourier transform is that I get a sampled version of this signal. So this is again delta functions and basically the same envelope, but I just have information here, nothing else. The Fourier transform is just an infinite copy of those. Remember, this is still the Fourier transform, right? This is still a continuous signal. All I have to do is just wipe out all these lobes. Then I'm done. Then I get this back. How do I wipe out all these other lobes? I just multiply it with this in the frequency domain. As long as I multiply it with this, I will always get back my original Fourier transform. And this is a rect function in the frequency domain. So in the time domain, this is going to be a sinc function. So if I convolve my sampled signal with a sinc function, I'll get the continuous signal back. Because convolving my sampled signal in the with a sinc function is the same as multiplying the Fourier transform of the continuous sampled signal, this one, with the Fourier transform of the sinc function, which is a rect, the rect will wipe out all these other lobes. All these other lobes will get wiped out. Only the first one remains. So you've got your Fourier transform back. You can take its inverse Fourier transform and get back the signal. Okay, so we actually have proven today the Nyquist theorem that you need to sample at greater than twice the maximum frequency content, and then you're guaranteed to recover the signal. So you have to just process it through an ideal low pass filter, which means this low pass just allows lower frequencies to pass and higher frequencies to get eliminated. So this is an ideal low pass filter. It's only allowing frequencies up to omega c and wiping out everything else. As long as this is between omega n and this, you're all set. Okay. So, so we'll stop here. This is quite a lot of stuff. So I'm hoping you guys are reading and catching up on this. So we'll probably be able to finish off the remaining whatever theoretical part is there and actually get back to our signal and then start with the practical applications in the class. Okay, so there won't be a class on Friday because it's a holiday. We'll again meet next Monday. So please take some time to read this so that you are back on, you're on top of all of this. Okay, so we'll stop now. I'll stop recording.